Okay, so for this problem, the problem statement is outlined here. We are going to have two spherical tanks with specific radii as well as areas, and it's going to have two holes, one draining out from tank 1 into tank 2, and our specific areas are underlined here, and they both have inlet flows as well and are in steady states. And the height of tank 1 will be 5, and then the height of tank 2 will be 3. But in this first video, we will be deriving the initial steady state equations, and that calculates the initial flow rates from leaving each tank. So we are going to do that for part A in this video. So we're going to first lay out our system. So we can see we have a tank right here, and we have a level of fluid right here, and we have a position 1 right here, and then we have fluid leaving this tank, and we'll just call this position 2. So what we first want to do is, our goal here is to calculate the two initial steady state flow rates, and we're going to be starting this from the Bernoulli's equation. So we have P2 minus P1, and this will be over rho, which is the density of fluid. And then we'll say plus acceleration due to gravity g, and then the difference of height z2 minus z1, and then plus our v2 squared minus v1 squared over 2, and this is equal to 0. So this will be our Bernoulli's equation in which we're going to start from. So as you can see in this figure I've drawn here, one of the tanks, we can see from position 1 to position 2 that there's no height change. So we basically say that z2 is equal to z1. So this cancels out. And then the next thing we're going to look at is we are going to say, what is v1? Well, so we can determine this. Basically, if you look at it, there's a small outlet hole right here, and you can see the cross-sectional area, which has to do with the relationship with flow rate. We can see the cross-sectional area right here is much larger than this spot. So we basically just say that the initial velocity is negligible, and we can say that the initial velocity is equal to 0, v1. And what we're going to want to do now is we need to calculate v2. So if we can see that there's a initial pressure P1 right here, and there's an initial pressure, and there's a final pressure P2 right here, or just a second pressure P2 right here in the system. And as you can see, P2 is going to the atmosphere. So we say P2 is equal to 0. And so if we put it back into our Bernoulli's equation, we have 0 minus, and P is equal to rho gh. Pressure is equal to rho times g times h. H is being the height of the fluid right here. So we have rho gh, and then over rho. And then we said that this right here is equal to 0. So then we just have, that leaves us with v2 squared over 2, because we also said that v1 was equal to 0 because of the difference in cross-sectional areas, and equals 0. So looking at this, we can cancel rho. So this leaves us with v2 equaling the square root of 2 times g times h, and h being the height of the fluid. So now what we want to do is set up our problem with two tanks in a series, two spherical tanks. So we have a tank right here. I'm just going to redraw the problem, and it has initial height h1 here, and then it flows over to it flows over to our second tank. Flows over to our second tank right here, and this is going to have a lower height because the fluid is initially flowing into this tank and then flowing to the other one. So the height on the first tank is going to be higher than the second tank. So we have our H2 right there, and this I'm going to just move that because we're going to draw some. So we'll just have our H2 right here. We'll call the height of that fluid H2, and this is going to be flowing out of that tank. And this is all steady state. So what we want to do is calculate initial flow rates for the leaving the first tank and the second tank. And we want to do that first by starting setting up our relationship for a flow rate. So we know that flow rate can be calculated if you multiply the area times the velocity. So we're going to call this one right here, we're just going to call this one Q12 because it is flowing from the first tank to the second tank. So we'll say this is equal to the area, cross-sectional area right here, from flow 1 to 2, tank 1 to tank 2, and times v, the velocity 1 to 2. But basically what we don't know is this velocity. How can we find that out? Well, basically if you look at it, we have an initial pressure right here in the beginning of the tank, and we have an initial pressure which is going to be leaving the tank, P2. So what we can think about is, how does the velocity, what is the driving force that will calculate the velocity? So if we set up what our pressure is equal, we can see that P1 is not equal. Sorry, we can see that P1 is equal to rho GH H1, and H1 is the height of the first tank, and we can see that P2 is equal to rho GH2, the height of the fluid of the second tank. So when you set up these two equations, you can see that the pressure difference, because you have up here we have P1 minus P2, or P2 minus P1, sorry, we can see the pressure difference is basically dependent on the change in height, because the rho and the g will cancel. So we basically can say that the pressure difference is based off the we say the pressure difference is based off the change in height between the two tanks. So we can say our V from tank 1 to tank 2, we can say that this will be equal to the square root of 2g, and then H1 minus H2. And usually in many equations we have H2 minus H1, but in this case, since the fluid is initially flowing into H1, the height will be larger. And we want to do H1 minus H2 in this case because we don't want to get a negative square root. So we have, this will be our initial flow rate for tank 1 to tank 2. So we have Q12 equals the cross-section area from 1 to 2, and then times our V1 to 2, which will be the square root of 2GH, and then times the H1 minus H2, because it is dependent on the change in height, the pressure is. And our next flow rate is a little bit easier to calculate, and this flow rate will be the one leaving tank 2. And like we derived earlier, we know that our velocity of tank 2, or our velocity of 2, is just the square root of 2GH. And we calculated that earlier in this video. So we can just say that our second initial flow rate is cross-section area 2 times V2, and then we can say that this is equal to A2 times the square root of 2GH. So we'll be using these equations to finish the problem in the next videos. But in the next video, just so you guys know where we're going, in the next video, basically what we're going to do is we're going to know these initial flow rates, but basically what we're going to need to find out is we're going to derive some differential equations, and this will show us how the fluid height in these tanks will change with time. So in the next video, part B, we will be doing that.